The slides are visible, right?
Yes, sir.
Okay. So and today we start discussing. So we in the last class we looked at these sequence labeling problems and how the statistical models can be useful for sequence labeling problems in NLP. And that has been one of the major approach that people followed until, let's say, 2010 or so, where this hidden marker model, conditional random fields have been very popular in NLP as a way to solve the sequence labeling problems. And in general, many Markov models have been used. For example, this task of language modeling, right? Right, where you want to model a language. And what is it meant by modeling a language? I need to understand how the words are generated in that language, and can I generate new sentences from the model which could understand that language, right? That is basically the language modeling. And the language modeling is important for several tasks in NLP, not only for just simply generating the languages, but also in tasks such as machine translation, or speech recognition or spell checking. Now, it is important to understand the way different words appears in a language. For example, if you look at this example, the amazing ladies and gentlemen in this class, right? So naturally, uh, nobody uses "and" in between ladies and gentlemen. Ladies and gentlemen, it should be "and," right? So it is that understanding that we should have about the language which will help us to solve several tasks like machine translation or spell checking. And that's what the language modeling does. So you studied about language modeling, right? Hello? Hello, can you hear
Sir.
me?
Yes, sir. What was the question? Can you please come again?
So have you studied language modeling?
Uh, that part yet to be covered, I think. Yeah.
Yes, sir. It's yet to be covered actually.
Is it to be covered? Sure.
Yeah. Profession Monandra is taking like I mean this part is we haven't been encountered this part in Profession Monandra's class, but I think it is a part of syllabus. So he will be covering that one. But still,
Okay.
uh,
So in the last class, we had covered up to the word representation, sir.
1 minute.
We covered the topic modeling though, but not the language modeling.
Penta models, bigram, trigram.
Yes, sir. We spoke about the bigram, unigram in the last class. Yes.
And what's the use of bigram, unigram? What do you think that is for?
It is basically to capture context.
We use this bigram diagram for word to vector training,
Yeah.
and also we use that representation, learn the word to vector representation. If that is language modeling, then yes. If not, then not sure.
Okay. So maybe I can just give a quick primer on what language modeling is. The word network is only learning a vector representation for the words, right? It doesn't tell you in what order the words has to appear. Does it?
Yeah, yes, sir.
Or
It
doesn't
is.
it? It doesn't, right? Yeah. So here we are dealing with in what order the words has to appear. How do you generate a sentence in a particular language? Okay. And see, understanding about what order the words has to appear is helpful in solving these tasks. For example, we saw this example of spell checking, right? So then maybe if you look at this, the tale of two cities. So it's unlikely a word like tale will appear among these words, right? It should be something like TALE. And that kind of understanding we get if we know the order in which the different words should appear in a sentence, right? So we need to get an idea about how these different words appear and or how these different words forms a sentence in a particular language. And the order in which the different words appears could be varying from one language to another language. Now, some languages will be following subject, verb, object order, like English. Some languages will be following subject, object, verb order, maybe the Hindi or Telugu, any languages or Indian languages. So that understanding is important for several tasks such as machine translation. We need to translate to some target language sentence. We need to understand the order in which the different words has to be arranged in the target language. And the statistical approaches to machine translation had two components. One is the translation model, which does this translation of words in one language to another language, and then language model, where the language model will arrange these words in the form which is expected to be in the target language. Okay, so that's about language modeling. So how do we do that? Okay, the idea is we can learn the order in which the word will appear, or some sort of a probability distribution over the order in which these words are appearing. Okay, so we can find out what's the probability of this sentence, the tale of two cities, and what's the probability of this sentence, the tale of two cities. And a language model which can have this knowledge about this order in which the words have to appear, it basically can tell me that, okay, the probability of this is going to be much higher than the probability of this quantity, right? Or the probability of this is going to be very small. So that is basically what we are trying to do in a language model. We try to learn the probability at which the words appear in some order. Okay. And how do we learn this probability? Okay. So this is what we want to learn in a language model, probability distribution over a word sequence, right? And if you know this probability distribution over the word sequence, we can now ask these kind of questions. What's the probability of this sentence? See if the probability of this sentence is going to be very small. Okay, there is some issue with this sentence. This sentence is not properly formed. If the probability is very high, the sentence is well-formed sentence. And not only that, we can make use of this. If you know this probability distribution, we can make use of this to conditionally generate a sentence, to generate a new sentence. This is learning some kind of distribution over the sequence of words, right? So if we have that kind of a generative model, which is modeling the probability distribution over your sentence, we can make use of that generative model to generate new sentences also. For instance, by making use of this conditional distribution. Okay. Of course, we know that we can obtain this conditional distribution if we know the joint distribution over all these sequence of words, right? We can write this conditional distribution as probability of W2, W3 up to Wk divided by probability of W2, W3 up to Wk minus 1. Okay. So we can, so the way you generate a new sentence is that, okay, you probably, to this model that you have, you probably give your first token. Okay, it could be a start token also, something like start of a sentence represented like this, start token, or it can be some word like the, or something, some word as a first word to this model. Okay? So let that be something like W1. And then the model can make use of this probability distribution to provide you the second word from this conditional probability of W2 given W1. And then the third word from the conditional W3 given W1, W2. And the final word from the conditional WK divided by W1, W2 up to some WK minus 1. That can be useful for generating new sentences also. So this is what the language model does. And now the thing is, how do I learn this probability distribution, right? And given some corpus, which is collection of documents, I can learn this probability distribution over sequence of words, right? But the issue is, if I just try to learn it over some very large sequence of words, like something like k length sequence of words, where k is something like 10 or 15 or something like that, then you find that for many possible combination of words, that combination of words will never appear in the corpus, and the probability is going to be 0. So you may not be able to generate many sentences which you have not seen in the corpus. So in order to model things, and in a more generalizable manner, people often go for some kind of a simplification or simplified model, which can model this probability. So ideally speaking, this model, which this probability distribution over all these sequence of words, you can write it as using this, the fundamental idea in probability. You can write it as something like probability of Wk given W1 to Wk minus 1 into probability of Wk minus 1 into probability of 1 to Wk minus 2, like that, up to probability of W2 given W1 and probability of W1, right? This is the exact way to write this joint distribution in terms of product of conditionals. But then, so this kind of exact modeling have drawbacks, as I mentioned, that may not be able to find out these all possible sequence of W1 to Wk minus 1 in your corpus. And more than that, the number of parameters that you may want to estimate is also going to be very, very large. So this is a situation similar to what we have discussed when we discussed about sequence labeling and while motivating hidden Markov model for sequence labeling task. Okay? So if you try to model the whole sequence y1 to yt, then the number of parameters that we might want to estimate is going to be very, very large, and you may not be able to find the whole sequence in the corpus at all. All these issues can come. So we went for a simplified model where we assume the joint distribution can be written as or assume some kind of a first order Markov model, and you write this joint distribution as something like P of y1 into P of y2 given y1 into P of y3 given y2, like that. A similar kind of assumption people make in the case of language modeling also, where you write these conditionals, you assume some sort of a first order or second order or third order Markov assumptions over these conditionals. So when you assume a first order Markov assumption, you assume that the current word, okay, this word that you have, current word, depends only on the previous word, WK minus 1, and not the words before that. So when you are modeling this conditional, according to first order Markov assumption, you say that WK minus 1 only depend upon WK minus 2 and not the other words, right? So according to a first order Markov assumption, you will end up writing this joint distribution as something like WK given WK minus 1, WK minus 1 given WK minus 2, up to some W2 given W1 into P of W1. Right? This is how you write by assuming a first order Markov assumption over this joint distribution. Okay. So this would simplify the model a lot. The number of parameters that you want to estimate will be much smaller because you're just modeling the conditional between two random variables. And secondly, there is no sparsity issues. You will always find out several possible combination of WK minus 1 WK in your corpus, unlike this situation. Okay, so now these kind of models, which make this first order Markov assumption, in modeling this language, they are generally known as bigram language models. Okay. So this assumption of current word depending upon previous word only and not on any other words before that is a bit too simplistic assumption, and many times you may not be able to model your sentences well by making this assumption, or you may not be able to generate sentences also well by using this assumption. So people might go for a second order Markov assumption where you assume these conditions will, like WK will depend upon K minus 1 and K minus 2. So you can write this joint distribution as probability of WK given WK minus 1, WK minus 2, probability of WK minus 2 given K minus 1, depending upon K minus 3, WK minus 2, up to some W3 given W2, W1, etc. Right? So here you are assuming that a current word depends upon the previous two words and not just the previous word. And this could be a slightly better model in terms of modeling the sentences and generating the sentences. And this is known as trigram language model. So these individual probabilities, you can always learn from the corpus, which is collection of documents that is given to you. And these probabilities of generating some WK given WK minus 1, WK minus 2 will be different for different collection of corpuses. Maybe for a collection of corpuses related to entertainment, it would be something, and related to sports, it will be a different thing, etc. Okay. So in general, you can think of a n-gram language model like this. Okay. So in an n-gram language model, you write these as something like probability of WK given K minus n, WK minus n plus 1, up to some WK minus 1. Okay, that is what a n-gram language model does. But in all these different language models, there are statistical language models where these conditional probabilities are computed from the data in a statistical manner using these probability estimates that we know for computing the probabilities, conditional probabilities from the data. Okay. So this is the basic idea behind language modeling. Is that clear?
Yes, sir.
Yes.
So are we going to cover the unigram bigram models in depth, or
It will be covered in some class.
okay?
I don't know, like I'm not sure if Professor Maranda would be covering because no, that's kind of a very new way of doing things which people don't use these days. So yeah, I'm not sure. You can check with Professor Maranda if he plans to cover it in some class. But it is in the syllabus, right? So it should be covered, I think.
Okay.
Sir, one question.
Okay.
So when we are generating this sequence of words, then how do we decide the value of k, where to stop? Like
Okay,
in the example,
in many
like
times, okay, when it comes to language modeling, people often consider some kind of a distribution over that k also, and people go for some sort of a Poisson distribution over that. I guess in the case of, I guess you studied LDA also in your, okay, latent Dirichlet allocation.
yes, sir.
And in LDA also, they have a generative model, right? And the generative model, they consider the number of tokens to be generated to be sampled from a Poisson distribution. So that K is typically modeled as a Poisson distribution.
So in the example, today is Tuesday. That probability is higher than Tuesday today is. For example, if somebody has given Tuesday today or today Tuesday, then we know that it should be today is Tuesday. So in that case, our the correct sequence of word has more, the length of that is more than what is actually given. So how do we know that how much extra word should we look for while generating the correct sentence?
I didn't get this with what you were talking with respect to this example. What is it?
Sir, for example, instead of Tuesday today is, somebody has given today Tuesday, which contains only two words, and we want to correct that sentence. So it should be today is Tuesday. So in this case, our input has a length 2, but the correct length of the output should be 3. So how to handle such situations here?
See, so the thing is, we are talking about generating, right? So when you talk about generating a sentence, uh, many times this length of the sentence is a user-defined parameter. People provide, okay, how length the sentence I should generate. While it can also be modeled as a distribution, like a Poisson distribution, and you sample that length. Uh, but no, this specific example is about whether this sentence is more favorable over the other sentence or not. So when you try to model the probability of uh, Tuesday today, then no, that, that conditional probability of a word appearing today if after Tuesday is going to be very small, and you don't favor this kind of a sentence. Okay? Well, if you look at this sentence, like today is Tuesday, that conditional probability is of the sequence of word appearing will be higher, and you favor that. But if you're asking this question, okay, I need to insert some word given some today and Tuesday. See, the idea is that you try inserting different words at different possible places, and and maybe like you see, okay, what word I should use if I try to insert some word here. Uh, okay, if you just consider these two, maybe one way is that you just see, okay, what word I should use if I try to generate a word here. Okay, maybe you try to see or you try to sample a word from the conditional probability of P of W given some Tuesday, and you end up sampling some word, which could be the most probable word which should follow Tuesday. And then you can think of sampling some word for here is, Tuesday, today, followed by, so we try to sample some word, probability of W given today. And you can think of just sampling some word here also, probability of some word given start symbol. See, in all these different combination of sampling at different positions will lead you to different sentences. And you can find out the probability associated with all these different sentences, and you can choose that sentence which is most probable. And the sentence which is going to be most probable would be something like Tuesday is today or something like that. So that is one way, and you can possibly recursively do this by trying to add more and more words at different positions and keep finding out the probability of that sentence. And you probably will stop when you find that adding more and more words is only going to decrease the probabilities and is not going to give you a good probability. That is probably another way that you can decide this. But of course, that also requires you to do some sort of a normalization over this length of the sentence. And that is what many scores that people use in language modeling does. For example, there is this perplexity score that people use. Okay. So the issue with the issue with simply computing this probability as conditional. Okay, so probability of W1 to WK as P of W2 given W1, P of W3 given W2, up to P of say WK given WK minus 1. One issue is that this probability can keep on going smaller and smaller as your length of the sentence becomes larger and larger, right? So to normalize it across the sentence length, one can consider some sort of a square root of, not square root, nth root or kth root in this case. Okay, so some sort of a kth root over this, which results in some sort of a normalized score, which could which doesn't depend upon the length of the sentence, and consequently you can use this score, which generally people call it as perplexity score. In fact, perplexity is like something like 1 divided by this quantity that I guess. As a way to evaluate the quality of the sentence.
Sir, another question, like when we generate a next sentence, next word, conditioned on the previous two word, we are not taking consideration of the order of the previous two word, right? So probability of generating Tuesday.
You are.
But we are just multiplying these two probabilities. So whether it appears in today is or is today, it will be same probability,
It
right?
depends upon the which order model you are using. If it is a bigram model, you are only conditioning with respect to the previous word. If it is a trigram model, you will be conditioning with respect to the previous two words. But that two words that you are considering, you consider the order in which they are appearing. So all these conditional probabilities, say WK given WK minus 2K minus 1, you compute it as, you count the number of times this order appears in the corpus, WK minus 2, WK minus 1, WK divided by, say, count number of times WK minus 2, WK minus 1 appears. So when you consider this, you see the exact sequence in which this word order has appeared in the corpus. You don't treat it as a bag of words kind of a model.
Okay. Yeah, yeah. If you consider bigram or diagram, then it is, yes. Yeah, it's clear for me, sir. Thank you.
Sure. All right. So yeah, with this background, you know, see, as I said, in this case, you compute this probability exactly by counting the number of times this sequence of words have appeared. Okay, and this is like a converting it empirically from the corpus, statistically from the corpus, and this may not be taking into account some complex ways in which different words depends upon each other, and no, it may not be generalizable to some sort of a unseen combination of words, right? So if you don't see some particular combination of words in the corpus, you can never generate that. The probability that you assign to that unseen combination of words is going to be zero, right? So, for example, in your corpus, you found there is a sentence something like today is Tuesday, but there is no sentence like today is Wednesday. Okay, so in your test data, if the sentence like today is Wednesday is appearing, then you may end up giving zero, probability of zero to something like today is Wednesday, right? But today is Wednesday is also a well-formed sentence, and it's also semantically correct sentence. So there shouldn't be, so we shouldn't assign a zero probability to that. So that kind of a understanding you will not be able to get by this statistical model, right? But if the model is capable of understanding that, okay, all these Tuesday, Wednesday, Thursday, Friday, they are all representing different days in a week. And if today is Tuesday is a well-formed sentence, then today is Wednesday also should be well-formed sentence and should be given a high probability. So the model should have that kind of an understanding, right? So in order to generalize well to some unseen sequence of words and unseen documents. So that is the motivation behind using neural networks for language modeling. And so we will be looking at not only a simple neural network, but some variants of neural networks used in language modeling, especially for sequence labeling problems. Some variants of neural network, which are like popularly known as recurrent neural network, have been found to be very, very useful. So we will be looking at those variants of recurrent neural network such as LSTMs, GRUs, and also we look at some convolutional neural network, how they can be used for modeling text data in this lecture. So start with, let us see how a simple feed-forward neural network can be useful for tasks such as language modeling. And this is one of the, yeah, of course, people have been using neural network for text classification for quite some time. But around early 2000, now Binge's group have proposed using neural networks for language modeling, which could take into account some kind of a semantics associated with the words also by learning some kind of a vector representation for words and doing language modeling. So if you look at the skipgram models and back of continuous skipgram models, word-to-vec models, basically word-to-vec model, whether skipgram or continuous back of words model. What was the goal there?
To get the vector representation of words.
Sure, but how are you trying to get that vector representation of words?
We were assuming we were initializing one input representation and output representation, and then through this for skipgram we were taking the conditional probabilities and then iteratively updating the weights to get the representation.
Right. So what was your neural network trying to do there? What was the input to the neural network? What was the output to the neural network? Let's say skipgram model.
Next word prediction.
Is it next word prediction?
Context.
Given
Prediction
given
based on what
I think it was given the center word. What are the surrounding words?
Huh. Given, see, there are two ways in which people do, right? Given the surrounding words, what is the center word, right? Given the
yes,
context, what is the word that you want to predict? Or given the word, how do you predict the context? These are the two ways people do try to learn vector representation for words, right?
yes,
So if you are given some W1, W2, W3, so one way is that, okay, I consider W1 and W3 as input. This forms my input. And I try to predict W2 using some neural network, right? And which approach is this?
this is continuous bag of word.
Huh. This is known as continuous backwards first approach, right?
Yes,
W. Yeah.
And now, if you try to predict the neighboring words, say you try to predict you're given W2, you try to predict W1, from W3 try to predict W1. So when you try to do this approach is known as skipgram approach, right? Yeah, so this is the way these neural network is trained to learn this vector representation for these words. But do you think these models can do language modeling?
You can give us the prediction given the word, what would be the surrounding words, or given the surrounding words, what would be the center words. But that loosely couples to the language modeling that we discussed, right?
Right. So they don't really do a language modeling like, well, see, you cannot form a well-formed probability out of them. So the probabilities that you end up getting is, so let us consider this case. The probabilities that you end up getting is something like probability of W2 given W1, W3, right?
Yeah.
So if you try to write this probability W1, W2 up to W3, W4, etc., using this model, you may have to write it as something like probability of W2 given W1, W2, probability of W3 given W2, W4, etc. And this is not a proper decomposition of the probability.
Sorry, this has the, or this does not have to.
This does not.
Okay.
Yeah. So what this neural probabilistic language model does is that, okay, it go for a language modeling task where it tries to predict, say, W2 from W1 or W3 from W1, W2, W4 from W1, W2, W3. So this is the way in which you write a probability distribution over the sequence of words, right? You can write it
Yes.
as conditionals as probability of W1 into W2 given W1 into W3 given W1 W2, etc., etc. And what it does is that it tries to predict each of these probabilities using a neural network. Okay. Rather than estimating this probability statistically from the data, what it does, it passes this W1, W2 as input to a neural network and try to obtain the probability of W3. Okay. And similarly, it passes W1, W2, W3 as input to the neural network and try to predict the probability of W4. So just like a n-gram language model, we may have to fix the number of inputs that can be passed as input to the neural network. So now if you consider some n-gram equivalent, then what this model, the neural network model consider is that the neural network model consider the last n words as input and try to predict the next word. Okay, that is an n-gram equivalent of a neural probabilistic language model does. Okay, so it's all about representing these probabilities or representing these probabilities using a neural network. Okay, that is what neural probabilistic language model does. While doing that, it also tries to learn a vector representation for these words. Okay, so when you pass these words as input to this neural network, what is the uh, traditional way in which the words are represented?
One hot vector encoding.
Yeah, one hot vector encoding, right? So
Yeah.
some encoding like 0, 0, 1, 0, 0, 0, something like that, where this is a v-dimensional vector. So that was how you could represent a word traditionally. But instead of representing the word as a one-hot vector representation, this neural probabilistic language model consider a dense vector representation, something like a d-dimensional dense vector, and along with learning the parameters of the neural network, they also learn these vector representation of the words. And because they learn some sort of a vector representation of the words, the model can generalize to sentences that it has not seen in the corpus. Okay. For example, there is a sentence like this: "The cat is walking in the bedroom." So of course that your corpus contains words such as dog, running, room, etc. But a sentence like this, "a dog is running in the room," did not appear as it is in the corpus. But the word dog appeared elsewhere in a different context, running appeared elsewhere in a different context, room appeared elsewhere in a different context, etc. But this sentence, "the cat is walking in the bedroom," appeared as it is. Okay. So you may end up learning some kind of a vector representation for all these different words. You will end up learning some vector representation for dog, room, etc. And it might end up learning that, okay, dog, cat, etc., they are all animals and they are domestic animals. And the vector representation for dog, cat, etc. will be closer, and maybe vector representation for room, bedroom, etc. will be closer. Vector representation for walking, running, etc. will be closer. They are representing some activities. So if there is a sentence like "the cat is walking in the bedroom," but there is no sentence like "a dog is running in the room," using these vector representations for these words, okay, it will be able to give a high probability to this sentence like "a dog is running in the room," even if this sentence itself hasn't appeared as it is in the corpus. Okay, so that is the kind of capability that a neural probabilistic language model will bring in by making use of a neural network to obtain these conditional probabilities, and also learning some kind of a vector representation for the words.
And sir, I have a question here. So this is only possible with the dense vector representation for finding the similar words like cat and dog, room, bedroom.
Right.
But not with the one hot vector encoding the traditional way, because there's no
Right.
similarity. Yeah. Okay.
Right. Yes.
Sir, one more question. Like in case of skip gram and bag of word, there also we did a neural network training and we predicted the center word. Here we are doing this next word. Is the only difference we are using dense vector instead of like one hot here?
No, in skipgram CBW, you're using a dense vector, right?
So there also we did neural network training, right? And here also
they
we are
also
doing.
use neural network training. They also use dense vector. The difference in the way you try to predict the or the task. So see the what task the neural network is solving. That is what is different. Okay? So this is basically the difference between these models. So we'll just
So there when it is predicting the center word, it also knows the future word, right? Here we are just using the next word. It doesn't have any context of the future word. So that should give the better representation. I mean, skip gram.
yes, it will give the better representation. That is true, and that is why for any general purpose task in NLP, people always go for a skipgram representation or CBW representation in word to vector representation. That is exactly the reason.
Okay.
So what will
So
be the
here,
dimension of
here the vector representation that you end up learning is tuned for the language modeling task. It may not be good enough for any general purpose task.
Okay. So if a word appears, then only it will be able to form that in the different context, right? I mean, dog should at least appear once in the
Yes.
corpus. Okay.
Right. Right.
And will it ensure semantic or syntactic structure?
Syntactic structure is ensured through these probabilities that you are learning, right? You're learning these conditional probabilities. WK conditioned on the previous K words. So that ensures this syntactic structure. And the semantics to some extent is captured through the vector representation of the words.
Okay.
Sir, what would be the size of the output layer here in the network?
We'll come to that. We are going to discuss this neural network structure. Okay. Yeah. So fundamentally, if you look at the difference in all this word-to-vec model and this model, the difference is in the task that the neural network is trying to solve, right? So if you look at CB of W, there what you're trying to model is probability of WT given WT minus 1 and WT plus 1. And you write it as, you try to obtain this probability by using a neural network. And neural network consider this WT minus 1 and WT plus 1 as input and try to predict the probability of WT, right? And in the case of skipgram, you try to model probability of some WT minus 1 given WT, again using a neural network which considers WT as input. And in this model, neural language model, what you try to do, the task here that you're trying to solve is probability of WT given WT minus 1 and WT minus 2, which you try to model as a function of neural network. The neural network consider WT minus 1, WT minus 1 and T minus 2. as input. Okay, this is how these models differ. Yeah, so now this is the task that neural language modeling is trying to solve. So it tries to simultaneously learn a function, basically a neural network, which can model this probability P of WT given WT minus 1 and WT minus 2, as well as learns a word embedding, a vector representation for words. And we'll see how it does this. Okay, so this is how it does. So now I'll assume for the time being, you have some kind of a vector representation for these words. So assume there is a dictionary, okay, a dictionary where you keep vector representation for all the words in your vocabulary. And if your sentence contains some particular words like the, cat, sad, on, that, you look at this dictionary and get the corresponding vector representations. Okay. And now what you do is that you pass this vector representation of the words. All right, so I think yeah, maybe in this particular example, okay, what you have here, this is the vector representation. What you have here is the vector representation, and you can think of getting that vector representation yeah. Okay, let me write that vector representation as this way I can write. Okay, so let me consider this matrix as some R matrix. Okay, and each element or each column, okay, represents some kind of a vector representation. Okay, so let us assume it is some 30 dimensional. Okay, this length of this column is something like 30 dimensional, or can be any arbitrary dimension. Okay, 50 dimensional or 100 dimensional, etc. So, but each column represents some vector representation for a word, right? So the first column represents vector representation for the first word in the vocabulary, right? Second represents a vector representation for the second word in the vocabulary, right? So like that, you have V words in the vocabulary. Last column represents some vector representation for the Vth column in the vocabulary. And this, I can just denote the whole vector representation over all the words in the vocabulary by some matrix R. And this R is going to be, if I assume each column or each vector is like 30 dimensional, R is going to be something like 30 cross V dimensional vector. Okay, 30 cross V dimensional vector. And now, here, to start with, what you're considering is a one-hot vector representation for a particular word, right? So this is going to be zeros everywhere. And at this place, it is going to be 1 and zeros elsewhere. So this word has 1 here and zeros elsewhere. So this has 1 here and zeros elsewhere, right? So this is like some sort of a one-hot vector representation for each of these words. And I can obtain the corresponding vector representation for this word by multiplying this R matrix with the on-hot vector representation, right? So if this is my on-hot vector representation, okay. For some word, let's say this is the on-hot vector representation for the fourth word, maybe that fourth word be cat, okay? So if I multiply this matrix R with this on-hot vector representation, I will end up getting that, this particular column, right? I will get this particular column, which is a vector representation for that word. Okay? And that operation is what is happening here. Okay? This is that operation. So you start with some on-hot vector representation for the word. You multiply that with this matrix R. That will give you a vector representation for these words. And see, in this model, the R is some sort of a weight matrix which is unknown to you, because when you start, you don't know what vector representations to use for each of these words, and you want to learn those vector representation, right? And that's why we are representing the operation in this way, where R is some sort of a assumed as a weight vector which is unknown to you, and you want to learn R also using the training procedure that is used for training the neural network. Okay, so once you have this vector representation for these input words that you have, then you pass it to a neural network and try and use that to predict your target word, that is the next word. Okay? And we'll see how exactly that happens. Okay, this is exactly how that happens. Okay, in this picture, that matrix R is apparently represented by C. Okay, so matrix C, which is representing that word embedding matrix that you want to learn. Okay, and at this point, here, what you have here is the vector representation for the something like t minus n plus 1th word. So this is the vector representation for t minus 2th word. This is the vector representation for t minus 1th word, right? And you pass these vector representations, you concatenate these vector representation and pass that as input to a neural network. And this is a fully connected neural network. Okay, this is a fully connected neural network. So these are the different operations you can think of what is happening. So you get these vector representation for each of these input words, concatenate them, and consider that as your input. Now, when you pass that as input to this neural network, so this is like a very simple neural network with just maybe like one layer or so, right? Maybe like 2 layers, maybe, or one layer. Yeah, one layer. So first, what happens is that you multiply this vector representation by some matrix H, right? By some matrix H, add some bias, and pass it through a nonlinear activation function, tan H activation function, to get some kind of a representation at first layer. And then you again multiply that with some matrix U. So this is what you get at the end of this. Okay? Here, H is the weight matrix that you use to multiply these representation that you have, which is represented by X. And then you pass it through a nonlinear activation function to get this representation, which is tan H of t plus H of X. Then you multiply that with some U. Okay? you to get an so the use is going to give you some kind of a real values that you want to associate with each of these different words that you can consider as your output. So what you're trying to model is probability of some WT given WT minus 1 up to some WT minus n plus 1, right? So this probability over WT, okay? So WT is the teeth word, and there are, if your vocabulary size is V, if your vocabulary size is V, there are V possible words in your vocabulary. Now now WT can take V possible values. Okay, so WT can take V possible values corresponding to each word in the vocabulary. And you want to find out what is the probability that WT is the first word, what's the probability that WT is second word, WT is third word, WT is fifth word, right? So you want to find out V probability distributions, right? You want to find out V probability distributions. And this is like a multi-class classification setup, right? Where there are one of V possible outputs are there, and you want to find out a probability distribution over V possible outcomes. And to find out a probability distribution over V possible outcomes, what do you do in the case of multi-class classification?
Sorry, sir, what's the question?
Softmax.
The previous probability.
So
We
if you
use
want to find out a probability distribution over V possible outcomes, okay, that is like doing a multi-class classification, right? How do you
Yes.
get that probability distribution?
we use
Softmax.
softmax function.
Softmax, yeah.
It's a softmax function, right? You use a softmax function. So if you can recollect how a softmax function is used in a logistic regression model, right? So you try to find out probability of the output y equal to some k given input x as something like exponential of wk transpose x divided by summation over all, let's say, j exponential of wj transpose x, right? This is what you do in the case of a logistic regression model, right? When you want to use it for multi-class classification. So you consider some k functions associated with k possible outcomes, and each function that you're considering is a linear function of x. Okay, it can be a nonlinear function of x also, but in general you consider it as a linear function of x. While okay, and in general you can write it as something like exponential of some fk of x divided by summation over all j exponential of some fj of x, right? And no, the different machine learning models differ in the way you model these FKs. In the case of a linear regression, you consider this as a simple linear transformation of x, something like WK transpose x. While in the case of a neural network, you consider this FK of x as a non-linear function of x, right? Which involves some linear transformation, non-linear transformation, again some linear transformation, non-linear transformation, etc. Right? So in this neural probabilistic language model, they are considering a very simple one-layer neural network, which just involves one nonlinear transformation. Okay? So that is what you are doing here. Okay, that's what you are doing here, where this is your input. You do a linear transformation followed by nonlinear transformation, and you multiply this with some u to get some v different possible values. Okay, so if we look at this dimension of x, okay, so the dimension of x depends upon what the dimension of each of these word vectors are. If I make an assumption that okay, each of these word vectors are something like 30 dimensional, and how many different past words I am considering 1 to n minus 1. I'm considering n minus 1 past words, right? So the length of this X is going to be something like n minus 1 times 30. So your H matrix will be working on this n minus 1 cross 30 dimensional input to get some latent representation, hidden representation. And let us assume that hidden representation is, let's say, 100 dimensional. So this hidden representation is something like 100 dimensional, right? So your H matrix, okay, the H matrix is going to be something like 100 cross n minus 1 into 30. Okay, so the H matrix maps this X to some 100-dimensional space, and you add some bias, and then you apply this nonlinear function. So what you end up getting here after nonlinear activation function tan H is a 100-dimensional dense, 100-dimensional hidden vector. Okay, and what you now do is that I want to, if you want to apply my softmax function over V possible to obtain a probability distribution over V possible words, I want to get some function value associated with each of these different possible words, right? To get a value associated with each of these different V possible words, I multiply this hidden vector by a matrix U. And this U matrix that you use, the dimension of that U matrix is going to be something like V cross 100. Okay, so when you multiply this U matrix with this hidden representation with this 100 dimensional, you will get some V dimensional vector, and each element of that V dimensional vector represents the function value that you can use into this softmax function computation. Okay, so in addition to the standard feed-forward neural network operation, they also have some kind of a skip connection where they try to have, they try to predict the output directly as a linear function of input X. And that is that additional skip connection that they maintain, something like this. Okay, but essentially this is what your this neural processing model is doing. It's a simple feed-forward neural network, and now the values that you end up getting here is passed through this softmax function to obtain the probability distribution over V possible words. Is that clear?
One question. So this U is the model parameter like which you have to train, I mean learn.
Right, right. U, H, all those are weight vectors that you want to learn. And how do you learn? You learn it by standard, the loss function that people use in neural network classification, right? Cross entropy loss function. So your cross entropy loss function is nothing but the maximum. It is nothing but the negative of the log likelihood, right? So this is the probability that you have. So you consider negative log probability, negative log likelihood is nothing but the kind of cross entropy loss that you typically use in training your neural network.
Sir,
And another question,
ahead.
this embeddings, whatever we are using, so it is pre-trained, right? I mean, so
No, you learn that. The embeddings that you use here, you will be learning that in this model. Again,
okay,
using the same loss function and backpropagating across these layers and finally to these representations also.
okay.
Sir,
Sir,
can you?
I have a question on the softmax side. So what's the classes there in the denominator in the summation?
This is the vocabulary size. That is, we are assuming V is your vocabulary size. There are V possible words. So the summation is our V possible words.
But the output size of the network, the dimension, that's just one word, right? Not all the vocabulary.
No, it is V. Here you are considering a U, which is V cross 100. So you'll be having V possible outcomes.
So we are having output of the whole vocabulary size.
See, finally, your output is going to be just one word, right?
Yeah.
How do you choose that one word? You choose that one word by computing the softmax, computing this probability distribution over all the v possible words and choosing that word which has maximum probability.
Okay. Okay, understood. Next question is this arrow, dotted arrow. It shows like skip connection from all those, right? But it's one skip connection, right? From the combined vector, not the
Right,
3 skip connection. Okay,
right, yeah.
thank you.
So, I have a question regarding the 10H. Is that the activation function that we are using in a regular neural network setup?
Right, yes.
Sir, can you explain once again the dimension part? Just a brief, like the input is each of the word is 30 dimensional vector.
Right.
So then we are applying the C matrix to it. So we are getting n.
No, the C matrix, after applying C matrix, you will get a 30-dimensional.
Yeah,
Let's say
30 dimensional representation for each word.
each word, yes.
So yeah, so it is going to be n minus 1 cross 30.
Right. Yes.
So then how is it the hidden representation you have written 100 cross n minus 1 into 30? So where is that 100 coming from?
That is my assumption that hidden representation is 100-dimensional.
Okay,
It can
okay,
be 200 or 300, anything else also.
okay.
So can we use any other activation function here, or 10H is?
We can use
Oh.
any other activation function also. Like this is one of the initial models which is proposed in 2003. So at that time, people just used 10H. That's it.
So when to use when? How would you decide?
That you can learn in a deep learning model, deep learning class.
Okay.
Sir, a generic query, sir. In case of skipgram and contiguous bag of words, right? They were not taking care of all the previous words, but in this approach, in neural probabilistic language model, it is intuitively sounding better, right? Because we are taking care of all the context, basically all the previous words.
But no,
So
you are only looking at the previous words. You're not looking at future words. Right? You're not looking at the entire context in the sense that okay, the words surrounding it, surrounding a particular word.
okay, yeah. So does those approaches still hold significance after these approaches came into fore?
No, this is one of the first approach. This is proposed in 2003. And those approaches were proposed in 2013, 2014 as a
Okay.
approach to learn a more general word, vector representation for words. So this vector representation that you have learned using this model was not general enough to be useful for other tasks. For example, if you want to do part of speech tag or sentiment analysis. Okay, this is useful for this language modeling task. So as a way to get a more generic representations, which can be useful for other tasks also, people came up with these continuous backup words and skipgram models somewhere around 2013, 2014, like that.
Okay. Thank you, sir.
Sir, but here in this case, we can always include the future words also, maybe one or two word, and include that into the network to get the representation.
But then your probability will not be well defined. So you are doing this in this way because of the specific way you write your probability distribution.
Okay.
But sir, like Varun also said, we can pass it, right? I mean, like, then it would be equivalent to the skipgram or the continuous back of words also.
Yes, it will be equivalent to that, so it won't be different from that. But then it won't be useful for language modeling because the way you generate language is that okay, you start with some word and then you try to generate next word from the current word, and based upon these two words, you try to generate next word. That is the way you try to generate a sentence, right? So if you are assuming that your model requires the future words also, then how will you generate a sentence? Generation process becomes difficult. But
But that
secondly,
also
when you
puts
have
to
that kind of model, your probability, you cannot write your probability distribution over a sequence in a well-defined manner, in the sense that it won't sum to one. It won't be a well-defined probability distribution.
Okay. But will that be the same case for continuous back of words also?
Continuous vagabonds is, we are not looking at the probability of a sentence at all. We are not trying to model, use it to model a sentence.
Got it.
It is just used for learning this vector representation.
Got it, sir. Yeah. Thank you.
Sir, one question. So whenever we have only one word, so that time the all other words, so we are taking care of all the previous words, right? While predicting the next word. So while doing the first or second word, so how we are going to pass the input parameter? Is it going to be 0 for all other case?
I didn't get that. What is it? It
So
will be 0. Yeah, it will be 0. Yes.
okay. Okay, thank you.
Sir, then if we have a sentence of length t, then iteratively we have to pass this network like a moving filter throughout the sentence to get.
Right.
Okay.
Yes. Okay, so yeah. So that's
Sir, just
yeah.
a question. Yeah, what is the benefit of having this skip connection here?
I don't see any benefit. It's generally required only if your network is very deep, like 10 layers or more. I don't know why they added it.
Sure. Thank you.
So, sir, for loss function where we are using cross entropy type, our output is also one hot encoded like target.
Yes, right.
Okay.
So here, when you train, you know exactly what the next word is, right? For that ground truth, it will be 1, and for the remaining words, it will be 0. So it's like what you suggested.
Okay.
All right. So now, let's see. So this is a very simple neural network, feed-forward neural network, and people have been happy using a feed-forward neural network for language modeling or text classification until 2011 or 12, right? And then what happened? Then what happened in 2011, 12?
CNN applications.
CNN came into picture, right? Vision community, they introduced all these AlexNet, VGGNet, all that, which they showed to surpass human intelligence, human capabilities in computer vision tasks. So then came this era of convolutional neural networks, and now the NLP community also started looking at how CNNs can be used for solving their problems, like text classification or sentiment classification or part of speech tagging, etc. Okay. So let's now look at how these convolutional neural networks can be used for text classification problems. Okay. What is the fundamental idea behind convolutional neural network?
Weight sharing through filter.
Weight sharing. What do you mean by weight sharing?
Like the many the connections between many neurons have same weights because we are using filters.
Reduced
Okay.
parameters.
Yeah.
So that
to
will reduce the number of parameters in
Yes.
a very high dimensional input, right?
Yes.
Sure. Okay, fine. Then what are these filters doing? What are these filters trying to capture?
The
Features.
spatial patterns.
So features are basically trying to capture some patterns, some cues, some features, extract some features which can be helpful for solving a task, right? And that has been found to be quite useful for solving several computer vision tasks. And people started looking at how this idea can be used in test classification also. Okay. And for some, let us say, so if you want to say, let us say, this task of sentiment classification, where say somebody gave you a review of a product, and I want to classify that review as positive or negative. Okay. So see, as a human, if I want to classify it as positive or negative, what will I do? I'll be looking for some particular features, some particular words are present in that or not, right? For example, if it is about some movie, then I will be looking at, okay, if somebody is, so somebody is saying that, oh, the movie is entertaining, fast-paced, thrilling, etc. So you're looking for the presence of some certain words in the text to help to figure out if it is a positive or a negative. And if there are some words like boring and slow and etc., then it will give you a cue, an idea that it's a kind of a negative sentence. So the idea is that, okay, can we use these kind of filters to figure out the presence of certain words being present or absent in the text, which can help us in doing solving these kind of classification tasks in NLP. Okay, and essentially, when on applied the CNNs and variants of CNNs, and that's what they figured out. They figured out that, okay, the filters are capable of identifying the presence or absence of certain words in the in the input sentence, which would help us eventually in doing a correct classification of the sentence into its corresponding class. Okay. And uh, no, well, see, the way people try to apply CNN for text data is the way similar to they applied it for uh, the image data. Okay, just like images, which is typically a matrix representation that you have as input, right? For text also, you can think of having some sort of a matrix representation by considering some vector representation of the words. Okay. So for example, if I have a sentence like, I like this movie very much, if that's the sentence I have, and I can consider this vector representation for each of those words in the sentence. And for example, in this example, I'm considering some 5-dimensional vector representation for first word I, 5-dimensional vector representation for second word like, etc., like 5-dimensional vector representation for much. And out of these 5-dimensional vector representation, by arranging or them one after the other, I will end up getting this matrix representation for the sentence. Okay. So you say first is to represent your input as a matrix, and this is how people represented your input sentence. They considered some vector representation for the words and represented this sentence as a matrix, something like a if there are n words and your vector representation is v, something like a n plus v representation. All right. So now Now what do? You apply some filter, okay, or over these different over this input representation that you have. But when you apply this filter over the input representation, now do you think any size filters can work here or would be meaningful here? Can I just simply use a 2x2 filter here or 3x3 filter here?
So can you repeat the question?
So I got some matrix represented for my input, and now when I want to apply some filter or perform, now I want to perform some convolution operation, right? Using some filter, right? So
Yes.
can that filter size be arbitrary, something like 3x3 or 2x2, or does those arbitrary filter sizes make meaningful in this context that we have?
Those small filter will not get the full context.
Yes, I think that will depend on the context.
We know how we are
If the
representing
context
the
size is larger, then we will choose the higher filters,
yeah,
higher
but we
large
know
size
how we are
filters.
representing the input, right? Our input is represented in a certain manner. Like if the number of word is n and a vector representation for each word is v, then we are representing to say n cross v matrix. So now this using some filter like 3x3 makes sense here.
I think we would want to look at the entire vector as such, so the v dimension should not change that.
Yeah, I think in this case, see, basically in the case of image also, when you apply a filter, it is applied across a region with spatially correlated or spatially closely related region, right? And that makes say 3x3 filter and all makes sense for a image because these different pixels in the images are spatially connected, and you can try to extract some features out of them. But in the case of this representation that you have, uh, that kind of neighborhood relationship holds at the level of this vector representation, that is across two vectors, or three vectors. If you look at three vectors represents three words which are which are closely located, three neighboring words, or maybe like four vectors, it represents four neighboring words. So now you want to apply this filter across like three vectors, or that is three neighboring words or four neighboring words, which corresponds to four vectors. So if you look at the filter sizes should be something like 3 cross V or 4 cross V of that form, right? It will be applied across the entire vector representation of a word rather than over some partial representation of the words. Yeah, at least initially this is the idea that people used in when designing the filters. The filters, they consider different sized filters like 2 cross V, 3 cross V, 4 cross V. A 2 cross V filter can be seen as going over every consecutive two words in the sentence and trying to extract some feature out of it. And 3 cross V filters can be seen as going over every three sequence of words in the sentence and trying to extract some feature out of it. Similarly, 4 cross V looks at a context of four words at once and try to extract some feature out of it like that. So this is what you have here. Okay. So these filters are something like 2 cross V size, and these are 3 cross V size, these are 4 cross V size, right? And you can apply these 2 cross V size over this input with straight length of 1 to extract these features. Again, this filter can be applied to extract these features. This filter will extract these features. This filter will extract these features, like that. Okay?
Sir, one question here.
Yeah.
Sir, then these matrix representations, which we are talking about, these have to be at max D cross V size, right? Dimension cross V size, maximum.
What is
Or
your D?
so in this case, D is equal to 5, right? In our example.
That is the length of the sentence, right?
Yes, sir. Yes. So these
Right.
matrix
Yes.
representations which are coming out, should these be minimum D cross V or maximum D cross V? Because we have seen the bottom matrices, right? They are less than D cross V.
They are filters. These are filters, right? The filter sizes you can keep varying depending upon how many sequence of words you want to consider
Yeah.
at a time,
Yeah.
right? So if you are
These
considering
filters are,
those,
yeah. So these filters are on the matrix representations, right? So those matrices would be D cross V, is it?
like this matrix is a D cross V matrix, assuming D is the length of the sentence. So
Okay.
this can be something like 2 cross V, 3 cross V, 5 cross V, etc. With maximum size will obviously be something like D cross V.
Sure, sir. See.
Yeah, so each of these filter will extract some features if you are seeing some straight length of 1. And then as in the standard CNN, you try to extract the most important feature by using this max pooling operation, concatenate them to get some kind of a representations after performing this convolution operation. And then that representation can be passed through a fully connected neural network to finally predict the class label associated with your input sentence. Okay, it can be, if it is sentiment classification, it will be like positive class or negative class. Yeah, so this is the kind of sequence of operations which is happening when you use a convolutional neural network for test classification problems. Okay. And which is very kind of a straightforward application of CNNs that has been used for images into this text data.
Sir, so all those filters are used at just one layer. I mean, on the same image, right? It's not like first layer and then next layer, because in one layer only the vector becomes like one dimensional because it is applied to the full length.
Right, yeah.
Okay. So always this kind of network will have only just one layer?
Not necessary. You can have multiple layers also. People may have tried with other variants of this also.
Okay. Thank you, sir.
And sir, how do we generally get this vector representation of word? Is it through word to vec or through the previous neural net that we saw?
Generally, people use word to vec.
Okay.
So at some point, people were using word to vec representation, and at some point, people using Elmore representation. Later, people using BART representation. Yeah. So those kind of general vector representations were people using to get this input representation.
Sir, I have a question. So the pooling operation that is done, is it one dimensional or two dimensional, sir?
I guess in this context, it is just one dimensional.
Okay, so the feature maps that we are going to get are always going to have the original vocab size dimension, is it, until the last layer?
But that depends upon the number of filters that you're using, right?
Yeah, that is true, but each feature map would always would be a v-dimensional uh, feature map, is it? Because if you're doing a one-dimensional max pooling, probably the number of rows would reduce, but the number of columns would always stay constant.
I didn't get that. What did you say?
So if all the kernels are of size v in terms of the width, and if you're doing a one-dimensional max pooling, if that pooling operation happens in the axis of the rows, that means all the feature maps would have v dimensions only because we are not pooling them in the dimension of the width.
Right. Yeah.
So my question is, until the last layer, would the feature maps always have a width of v? Is that a right statement?
If you're asking about this width of this feature map here, that depends on
Yeah,
the
yeah.
features that you use, right? Number of filters that you use, right?
Yeah, but each feature map would be of size v, is it?
That's before pulling. After pulling, it will be just one, I think.
Before pooling, it depends upon the stride length also. No, if your stride length is, it depends upon the size of this filter also. Maybe you can think of something like V length if your filter size is 2 and stride length of 1. If your stride length is higher, that size will be even smaller, right?
Yeah, but here the stride is also one-dimensional, right, sir? So, and the pooling is also, I'm assuming, is across rows. I mean, maybe we'll club, if we say it is across two rows, maybe we just take uh, one that maximizes between two rows, but the width is always staying constant because we are not pooling across two dimensions.
Sure.
Yeah, so my point is, I think as we go deep into the layers, the number of rows would keep decreasing, but the width of each feature map would always stay constant if the pooling operation is just one dimensional.
Okay. Yeah. Okay, so let's get into this. Yeah, this is just what it is learning. Okay, for example, when you use this model for uh, sentiment classification, I guess for sentiment classification. See, so you end up learning some filters, and if you look at what are the sequence of words which is uh, given a very high value by certain filter. Okay, they found that okay, maybe a filter which is trying to extract some positive presence of positive words. They try to give very high values for sequence of words like these, which represent some positive aspects about some review. While another filter tried to extract some negative aspects about the reviews. It gave very high value for some sequence of words like this, which considers some kind of a negative aspects about some review. Okay, so this is a simple a way in which the CNNs can be used for text classification. Okay, so now one question would be how we can use this for part of speech tag, right? What do you think could be a way? Maybe you can think about it, how you can use CNNs for part of speech tagging. But the point is that when it comes to part of speech tagging, right, you are not giving a label for the entire sequence of words, right? You want to give a label for each word in the sentence. So how you can modify or come up with a CNN model for part of speech tagging is something that you can think about. Yeah, so see some of these see if you look at this way in which these CNNs have been used, you always have to design a filter which is of something like 2 cross V or 3 cross V like that. Okay. And when you have a 3 cross V filter, it will be looking over all these subsequences, three or 3 word subsequences in the sentence and trying to extract some feature out of it. So at that time, it only look at a subsequence of length 3. Okay? It cannot look beyond that to extract something out of it. But many times, there will be some long range dependencies that would exist in the sentences. Okay. And that kind of long range dependencies that would be existing in the sentences cannot be captured using these CNN models. So if for example, if you use a very large filter, maybe like a 10 cross V size filter, which can possibly capture some kind of dependencies across a 10 length subsequence, then the number of parameters becomes very, very large. And the number of parameters that you want to learn, estimate becomes very large, possibly resulting in overfitting and other issues. So it is not very, it cannot efficiently in the, capture some kind of a long range dependencies by using smaller size filters. And that could be a problem for certain applications, maybe for machine translation or some other summarization kind of applications where there could be some kind of a long range dependencies that could exist. The CNNs might fail to capture that.
So can we increase the number of layers in that case? That will capture more longer context.
Uh, Perhaps it could capture. Maybe it could capture, yeah.
So that could be one solution to capture longer range.
Yeah, maybe there's a possibility that you can consider multiple sequence of convolution operations in a way to capture that.
Yes.
Yeah, but again, those will further increase the number of parameters that you want to estimate in the model. Parameter efficiency is a issue in that case. Yeah. So, but no, the way in which there's some kind of a neuro science related aspects also into it. The way the human looks at text and understand the text. Okay? The way in which the humans read text, they read text from uh, say, I mean, depends upon the language, and in most of the languages, you read text from left to right. And as you keep as you keep reading from left to right, you go over the sequence of words in that order. And within your mind, you maintain some sort of a summary of what you have seen so far. No? It could be if it is like a sentence, or if it is like a paragraph, or even a document. You just keep reading from left to right in some particular order, and you maintain a summary of what you have seen so far, which you make use of answering some questions or summarization or translations, etc. Right? So now the question was, okay, can we come up with some kind of a neural network which is capable of mimicking that and can also learn things in a much parameter efficient manner? Okay, and that led to the use of recurrent neural networks for solving problems in NLP. Okay, so now there are one issue is that, okay, recurrent neural networks can model the way in which the human process text data, and second, many times this text data involves sentences of varying length. Okay? And the recurrent neural networks can easily work on text data of varying length without any additional cost or additional without any change in the internal representations. So it can naturally process a varying length inputs. That is another advantage in using a recurrent neural network for text data. And it can, so theoretically speaking, it can capture long-range dependencies. Well, practically speaking, people found the vanilla recurrent neural networks were not able to capture long-range dependencies and came up with some variants of recurrent neural networks such as LSTM, GRUs, etc., which is capable of capturing some long-range dependencies. But theoretically speaking, they are capable of capturing long-range dependencies, which can be useful for several NLP tasks, including machine translation or summarization, etc. Okay, and this is in a nutshell how you can think of a recurrent neural network works. Okay? So the recurrent neural networks, they consider these different words in a sentence in a sequential manner, one after the other, maintaining a hidden representations for each of the words it sees in the sequence. Okay, and the hidden representation that it learns at any time t depends upon that word that it sees at that time, as well as the hidden representation at the previous time. So it recursively captures this dependence with the words it has seen in the past. Okay, and that is what you can see here. So for a word I, okay, you consider some kind of a vector representation, and your recurrent neural network consider that vector representation and form some hidden representation, and then for the next word, you consider that vector representation of the word as well as the previous hidden representation and form a hidden representation uh, for time 2. And then again, for the next word, you consider that vector representation of the word and the previous hidden representation and form a new hidden representation. So you are forming this in a recursive manner. We'll see this various steps involved in a recurrent neural network in forming this hidden representation. But you essentially form this hidden representation in a recursive manner, so you capture the dependence with what you have seen in the past, and eventually, whatever hidden representation that you have finally have will be used for some text classification or some kind of a summarization or language translations, etc. So more specifically, if you look at these operations which are involved, these are the various operations involved. So you can you have some input xt at time t. That input xt at time t is transformed using some weight vector w to get some representation w times xt. Then it is combined with some transformation of the previous hidden state also. So here you have this previous hidden state represented as ht minus 1. So that is multiplied with this weight vector u times ht minus 1. Then you combine these two and pass it through a nonlinear activation function g to obtain some hidden representation at time t. Okay, so it recursively considers the hidden representations in forming new hidden representation and maintains some dependencies with the past data. And now, once you have these hidden representations, so in this example, I'm just considering a one-layer recurrent neural network where you just have one layer transformations, and this hidden representation is then multiplied with another vector v, and then it is used for making getting the probability distribution over the outputs. Possibly you can think of this f as some sort of a soft max function or something like a logistic function, which will help you to get some kind of a probability distribution over possible outputs. Oh, sorry, I think, yeah, softmax function is here, right? Yeah, so f is nothing but a softmax function, yeah. So f can be seen as a softmax function or a logistic function, which can help you to get some probability distribution over the outputs. All right, so this is a very simple recurrent neural network. Is that clear?
Yes, sir.
Sir, why are we using same U and W across the layer here?
Because then it will be uh, insensitive to the length of the sentence. So if you are maintaining a different U and V, then it will depend upon the length of the sentence. And as many times the sentence length will keep on varying, and maintaining a different U and V for each of these positions, etc., will make it difficult to scale it to arbitrary length sentences. And people have found also that you don't really need to have a position dependent weight parameters. You can have these weight parameters which are position independent, and that's most of the times is sufficient to capture the dependencies and model things.
But sir, when we read long document, then as we go along, then generally the summary that we keep in understanding the document changes as we go along the document. So by keeping U and W same across the network, so in this case, aren't we uh, like giving equal weightages to all the hidden information and current information, irrespective of what we have summarized so far?
Right, and generally it could happen that with a standard recurrent neural network like this, if your input is a very long sentence like a document, it could happen that you might end up forgetting what you have seen in the uh, initial part of the document. But the problem with maintaining a position dependent U and W is that it will overfit and it might not generalize well to some unseen documents. It could happen that for a particular sentence, maybe like, so let's say the sentence length is 10, and maybe like uh, so eighth and ninth word is very important for the task that we want to have. Maybe for some other test sentence, it could be like first and second word. So many times, we having maintaining a separate parameters for different positions in the sentence or positions in whatever time series data that you have may not be helpful from a generalization perspective. But rather, one can think of making some modification to the hidden state as a function of the current input that you are seeing. Maybe like some of the words may not be important, and for those words, you don't change your hidden states that you have seen so far. And for those words which are important, you try to change your hidden state. And that is something what some variants of recurrent neural networks like LSTMs and GRUs are trying to do. Okay, so maybe like in a sentence, which is a long sentence, maybe there'll be some words which you have seen initially will be super important, and some words which you have seen later, maybe it could be some kind of a stop words, or it could be some kind of a words which are not useful for sentiment classification. And no, it's better that you don't change or modify the hidden states if you encounter those kind of words, but only change you if you encounter some important words. So how to bring that kind of context dependent modification uh, into the hidden states is what the models like LSTMs and GRUs and variants of recurrent neural networks are trying to do.
But in this network also, can we say that these hidden representations are nothing but the modified vector representation of the same word? And does it take the context also into the account? Because
The standard
it
recurrent
is,
neural
yeah.
network doesn't, right? Yeah, maybe to some extent it might be able to. Maybe for some words, this XT, W times XT could be, I don't know, like some small value, but no, it is bit difficult to really manage that with these simple operations of a recurrent neural network.
Okay, thanks, sir.
So, sir, in case of CNN, the filter was able to look at the three words together, right? And here we are training each and every word. So, one by one, what do we like? Can we have kind of filter itself, and then we apply whole this idea on the whole filter, like taking the previous state and then use and add it in the next one.
Yes, that you can do. You can have something like a CNN LSTM model or CNN RNN model, where you can first apply some filter to extract some relevant features. Then you can have an RNN model over those extracted features, which will capture these dependence in some way. Yes. But no, such kind of complex models are typically not used uh, in NLP, but there are some problems. Some, for example, video data where you have a sequence of frames that you see over time, or maybe some other uh, time series image data where people have tried using CNN, RNN, or CNN LSTM models.
Okay.
All right, so yeah, so see, these are some of the advantages which you already mentioned. It can capture some inherent sequential nature present in the language. Can model variable length text. Yeah. So this, yeah, RNN for language modeling. Well, yeah, this is how you can use RNNs. So the previous neural network that we have used was a simple feed-forward neural network where you are required to pass all the last, uh, you know, uh, n minus 1 words as input. And there you need to assume, you can make an assumption on the n-gram modeling, right? For example, I am saying that I am going to predict my W K only based upon last n minus 1 words. I need to make an assumption like that when they want to use a fully connected neural network for language modeling, as we have seen in the the first model. No, but ideally, the kth word prediction will depend upon all the previous words, and a using a fully connected neural network, we may not be able to model such a situation. But here, using a recurrent neural network, we can capture that. We can capture this dependency with arbitrary length past words and try to predict the next word by capturing the dependencies with all the previous words. That kind of a modeling is possible with a recurrent neural network. And this is an example where how you can use this recurrent neural network in doing language modeling. Okay, so where if you're trying to predict for this word, you may use the previously predicted word as well as a hidden representation, which is a function of all the previous words, and make use of this in predicting the next word. So you capture this dependence with all the previous words using a RNN model when you use it for language modeling. Okay. So the RNS models can be naturally used for other tasks in NLP, like the sequence labeling task that we have seen uh, in the in the in the last class, right? We saw the sequence labeling problem, and for instance, now you can have so this is your input sentence, and this is the output that you want to predict, which is the part of speech tag, right? Part of speech tag, NNP, MT, VP, DT, NN, etc. So you form some vector representation for each of these words, right? This is the vector representation for these words. Then you pass it to a RNN, right? And maybe for the first word, you just get this hidden representation based upon this input alone, and then try to obtain this probability distribution over part of speech tags. And for the second word, when you form this hidden representation, it takes into account this word as well as it depends upon the previous hidden representation, thereby capturing the dependence with the previous word. And then you can predict your part of speech tag based upon this probability distribution. And now for the next word, again, you consider this vector representation and previous hidden representation and make use of this previous hidden representation, which in turn is a function of the hidden representation before it, and thereby take into account the dependence with all the previous words in predicting this part of speech tag over this word. So this is the way one can make use of this RNN for performing part of speech tagging. And the way you train RNN is that you will be having a error or the loss function that you compute for each of these different part of speech tag that it predicts. Okay, you can compute a loss function, and then you can do a backpropagation over time to learn these different parameters. Here we have considered these parameters U, W, P, all that, right? So this is W, U, V. Okay, so you can learn all these parameters by doing a backpropagation over time. So how to do a backpropagation over time, you can learn in the deep learning course. Or what is this current? What have you learned about RNNs in deep learning?
Not yet, sir.
Okay, what's the current topic which is taught?
So we are actually going through the back propagation,
Okay,
and
sure.
in the
Fine,
last
fine.
class we covered the back propagation part here.
Okay, fine, sure. Yeah, so there is for RNNs, people use this backpropagation through time. over all the sequences that you have seen to learn these parameters, which you can learn in that deep learning course. And yeah, so if it is some task like sentiment analysis or something like some other test classification task, then you look at all these sequence of words, obtain a hidden representation and get the final hidden representation out of the final word, and then just use that final hidden representation to predict the sentence category. Okay, that is how you can use it for simple test classification. Okay. Yeah, so see, many times you can see that if you just use a simple RNN, it will be looking at the words in one particular order, right? But there could be some information that you can make use of in predicting the part of speech tag, for instance, if you start looking from the word in the reverse order. Okay, so maybe if you want to predict, so what is the part of speech tag is going to be for this particular word. Okay, if you just run a RNA, it will be running in this order, starting from the first word, second word, third word. It tries to see what the part of speech tag is going to be. In this case, it only takes into account the dependence on the first two words. Okay, but if there is a way we can capture the dependence with respect to the later words also, then we may be able to predict this part of speech tag better. So how we can make use of an RNN to do that? Okay, so that idea, so that thought led to something called bidirectional recurrent neural network. And the idea behind bidirectional recurrent neural network is very simple. You run a RNN model in the left to right direction as you do normally. And then what you do, you take your input data, reverse the words in the input data, and run an RNN on that. That basically means that you're running a second RNN on uh, uh, right to left direction. Okay, so you run a second RNN in right to left direction, and you run first RNN on left to right direction. And then what you do is that you combine the hidden representations obtained from first RNN and second RNN. So here you try to combine the hidden representation. So when you combine this hidden representation from first RNN captures the dependence with the previous words. The hidden representation from the second RNN captures the dependence with the later words. And so you have a much better context or hidden representation that is available, which you can make use of in predicting this output, maybe like part of speech tag. So this is the idea behind bidirectional RNN, and people have found that to give a much better, not much better, maybe like relatively better performance than standard RNN in several natural language processing tasks. All right, so this is kind of a story about RNNs, and RNN story is not at over. There are still some things we need to discuss. And maybe we can think of discussing those things in the next class. And we can stop here for today. Any questions do you have on what we have discussed so far?
Yes, sir. Sir, we discussed that RNN are better at handling varying length inputs sequences, right? So compared to CNN or other neural network traditional approach. So is it because of the fact that it takes into all the T minus all the past words into consideration? Is that the only reason why it is able to handle varying length better, or there is more to it?
Because of this recurrence in the way it models the function, right? So it recursively models the hidden states. And if you can see, you see that in many of these RNN implication, RNN models, we don't consider these weight vectors to be position dependent. So we use the same weight vectors U, W, V in computing the hidden representations at any time t, right? So it can naturally deal with arbitrary length sentences. But the moment you make this UWV dependent on time t at which you are looking at the input, then it may be difficult to for this RNN to deal with arbitrary length sentences.
Sorry, sir.
You can still deal with arbitrary length sentences by not considering some UVTs, etc. But it becomes a bit more complicated.
So if all these weight vectors are not dependent on time t, then it's able to handle, is it?
Right.
Very.
Yes. Yeah.
Yeah.
Sir, one question on bidirectional LST, sorry, RNN. So there we saw that it is combining the hidden state. That's the output from the both RNN, right? Or is there any communication even between these two RNN? Like, are they using hidden state? Like RNN1 is using hidden state from RNN2. Is there any communication among them?
No, no. But when you do a backpropagation, you see, there is a error which is backpropagated
Oh,
to both these RNN1 and RNN2, and that error comes from the same output that you are trying to predict. So in that way, you can see some sort of an indirect dependence between what you're learning in RNN1 and RNN2. But otherwise, there's no direct connections between them.
got it, sir. Thank you.
And sir, in bidirectional RNN, the initial vector representation of words remains same in both the direction.
Right.
Right.
Yes. Yeah.
Sir, what to interpret from hidden states at different time step?
For which case?
In general, in RNN we have hidden states
Huh.
at each time step.
You can
So
think
what
of it as
what
a summary of what you have seen so far.
okay.
So you have seen some sequence of words. It's a representation of the summary of all the words that you have seen so far.
So in a way, it is similar to the max pooling operation in that context. What we do in CNN.
Max pooling, just select one of them, right? So
Yeah, but
this
the idea
just
behind
not.
is summarizing, right?
It's a summary, but it's like you just select one of them rather than maintaining a dependence with all of them. Here, your HT will capture some sort of a dependence with all the words that you have seen so far. It's not that, it is just selecting the best possible word or best possible path that you have seen so far.
So if instead of max pooling, it's average pooling, then can we say it's the same thing?
Mm. Well, maybe it will be more closer, but you see that, yeah, maybe it will be more closer, probably.
Okay, sir.
But this is what it is, right? It is, yeah. So Arun tried to create a composition of an arbitrary long sentence along with the unbounded context. But the thing is that with the uh, uh, yeah, maybe, I don't know, like, yeah. So this aspect, try to extract the most important n-gram, comes into picture when you use a max pooling. Yeah, maybe with our average pooling, it could be average of all the words, right? So maybe, I don't know, possibly it can be closer to some hidden representation.
Yeah, I think in the shorter length, no, because it just cannot handle the longer length. So it's inherently different, but little bit similar.
Yeah.
Sir, in a different context, let us say I have a data set. Uh, I want to model the what is the health of a crop or agriculture situation at different month or at different fortnight level, and so these are sequential learning task in a way, because health of a crop at any time step depends what was the condition before it. So, and
Sure.
I know that at each time step, my input variables are what is the temperature condition at that time, and how was the rainfall condition, and what is the wind speed, etc. So if in a way, if somehow I represent each of the conditions like temperature condition, wind condition, and rainfall condition in vectorized way of d dimension. So how to model such problem using RNN, because here our input representation will be like 3 cross d, not 1 cross d for each
No, but
instance.
D is the time that you are talking about, right?
D is a, like, let's say, vector representation. Let's say I am representing high rainfall using a 3-dimensional vector or 4-dimensional vector. Similarly, temperature using a 4-dimensional vector. Like in the case of word vec, we represent each word with some D dimensions. So if we replace the word with the temperature or wind or rainfall condition, so we have a D-dimensional representation for each of these parameters. So
Okay.
then
And
how
you
to,
have
I was
these
just,
over
yes,
some period of time, right?
yes, sir.
And what is that you're trying to predict?
I'm trying to predict the condition of crop or condition whether the health is good or average, like I have 5 different classes. So
So
this
you
I want
can,
to predict.
so for each of these time steps, this representation of temperature, rainfall, etc., you can consider as a vector by concatenating all these individual representations.
Yeah.
And you can consider this vector representation over multiple time steps as an input to a recurrent neural network, right?
Yeah.
And you can predict this, you have this data condition of the crop as your output, which you can use to train your recurrent neural network. And then you can use this for predicting, predicting, assuming that, okay, you are given some sequence, that means your observations from last 4 months, how my crop condition is going to be in the next month. So those kind of
Yeah.
questions can be answered using a recurrent neural network by training on that sequence data that you have.
So it means that if we have different layers of information, so better to concatenate them and make a single vector
I
rather than,
don't see that's a better way. Coordinating may not be a better way. You see if you have these data from different sensors, maybe you can probably get a I don't know, like these are not big data, I mean high dimensional data, right? These are anyway like 3-dimensional, 4-dimensional. So in which case you don't have to apply another neural network transformation over each of these to get some representation and then concatenate it. Maybe just simply concatenating them would be good enough. But that is something you need to try it out. Whether you need to treat each of these different data coming from each of these different sources in slightly different way, or just concatenating should work or not.
Okay. Thank you, sir.
All right, so we will stop here for today, and then we'll meet again sometime.
Yeah.
Probably
So
mark
we
in
have
the
class on next Saturday, sir. In the schedule, don't see it.
schedule. It's there, right? No.
17th
For
Feb.
my class is not there, but
Oh.
I thought Professor Monendra have kept. No?
At least I can't see. Others can comment if they're able to. Yeah.
I see. It's not there. 17th February. It is not there. Next year is 24th February, I guess.
Okay, sir. Okay. Yeah.
Sure.
Thank you, sir.
Okay.
Thank you, sir.
Yes, sir. Thank you, sir.